Hello everyone. Welcome to part 1 in our series on solving differential equations using Laplace transforms. Today we're going to be talking about transforms and specifically about the Laplace transform, what a transform is and what exactly we can do with it. Okay, what is a transform? Let's first start with something a little more familiar, the function. What is a function? Remember that a function is some kind of engine or machine, if you want, that converts from a number, let's call it x. So this is a number. We input that into our function. What does the function do with it? It churns out another number, commonly called y. So a function basically converts from one number to a different number, or even possibly the same number, but it does something to the input and produces an output number. Well, a transform you can also think of in terms of some kind of conversion machine or engine. It converts from a function, which we're going to call f, into a new function that we'll call capital F. So a function converts from a number to another number. A transform converts from a function to another function. And by convention, we usually use a lowercase letter for the input. We use an uppercase letter for the output. But either way, these are both functions. Input function, output function. Okay, before we get to Laplace transforms in particular, I'm just going to do a very brief review of improper integrals. Hopefully a 2-minute review will be enough. If not, you may want to review on your own. Okay, here we go. Let's say that I want to integrate e to the minus x dx from 0 to some number. Let's say it's b. Okay, what does this look like geometrically? You may remember that an integral like this is equivalent to the area under the curve of y equals e to the minus x from 0 to b. And if I just do a rough sketch over here, remember what the exponential function looks like, maybe something like this. This is y equals 1, and then this curve goes off to infinity. It'll get closer and closer to the x-axis, never quite touching the x-axis. This integral is the area under that curve from 0 to some number b, which we'll assume is a positive number. Let's say that b is right here. This integral gives us this area right here. Now, we might want to know what happens if b becomes very large. That's what we call an improper integral. That would be the limit of this integral as b goes to infinity. Now that's the strict mathematical precise definition of an improper integral. A shorthand notation for this integral is this. It's not exactly precisely defined because infinity is not a number, so we can't have it as the upper limit of an integral. But this is commonly used notation for this limit. How do we do an integral like this? Well, we kind of barrel ahead. We do the integral. What is the integral of e to the minus x? It's just minus e to the minus x. And we're going to evaluate it over these bounds. Okay, what does this mean again? This means let x approach infinity. What do we get? As x approaches infinity, the exponential goes to 0. So my upper bound gives me minus 0. Then I subtract the value of this function at 0. Well, that's minus 1. So that means I'm going to get a plus 1. My final answer is 1. So in some strange way, right, this infinite area, right, it has an infinite extent, actually has a number associated with it. It's actually 1. The bigger I make b, if I keep calculating this integral, I'm going to get a number which is closer and closer to 1. So in the limit, as b approaches infinity, I get 1. This is kind of just pointing out that even though this has an infinite extent, these integrals can exist. If this limit doesn't exist, we say the improper integral diverges. That just basically means the integral doesn't exist. Okay, that was my quick review of improper integrals. Now let's actually look at what the Laplace transform actually is. Here we go. Traditionally, we use this kind of painful notation. We've got this curly L. It's meant to stand for Laplace. Curly brackets. This function is the function that's going into the transform. That's our input function. Here's the definition of it. This would be the strict definition. So we take the limit as b goes to infinity. Integral 0 to b. The function, and we're going to use t as our variable, times e to the minus st dt. That is the definition of the Laplace transform right there. And as usual, we can use shorthand notation for this. This is what it looks like. Now, let's look at this. T is the integral variable. Right? We're going to plug in, using our upper and lower bound, we're going to plug in values for t once we've integrated this. T will disappear. S will still remain. So this will be a function of s. And traditionally, we use uppercase F and the variable s. We could use any other letter besides s. Some people might use x here. We've got a function of x. But the important thing is that this is a function of this variable that shows up right there. That is the Laplace transform in shorthand notation right there. For a function little f, the transform gives us a function big F. And this integral may or may not exist. It depends on whether this limit exists or not. Depends on what we put here. And it only may exist for certain values of s. Okay. Let's actually try an example Laplace transform to see what we actually get. Otherwise, this is all very theoretical. Okay, what function am I going to use here? I think it's best to start with a nice simple function. So here's our input function, and conventionally we use t as the variable, as the independent variable for our function. Okay, but I'm not even going to use a function as complicated as that. I'm going to use the constant function. Okay, here c is any real number. Could be positive, negative, could even be 0. And I want to know what is the Laplace transform of this function. Well, let's use our definition. The Laplace transform equals the improper integral, okay, the function little f times e to the minus st dt, and we have to integrate that from 0 to infinity. Okay, well, we know how to do integrals like this. C comes out. Okay, what is that integral? In this integral, which is a t integral, s, even though it's a variable for this function, s is considered like a constant. This could be any number, 5, 12, 15. So we actually can integrate this fairly easily. It's like e to the minus 5t dt, except that we're using s instead of 5. Okay. Well, the integral of that is e to the minus st over minus s, evaluated from 0 to infinity. We'll move that over to make sure I have enough room. Okay. Well, the c stays there. The s is constant. I'm going to pull it out like this. Okay. Remember, this means we let t approach infinity. What happens to e to the minus st as t approaches infinity? Well, assuming that s is positive, then we have e to some negative large number like minus a billion, minus a trillion, etc., etc. That's going to go to 0. So I put 0 here. Minus. Okay, plugging in t equals 0, well, our exponential just becomes 1. So we get 1. Okay, 0 minus 1 is minus 1 times minus c over s. I get c over s. That is the Laplace transform of the constant function little f equals c. And we have to put a little qualifier here. This only works if s is greater than 0. If s here is negative, this exponential goes off to infinity. That's it. That is the Laplace transform of a constant function. Next time we'll see what we actually do with these Laplace transforms in terms of differential equations. Well, that's it for this video. I hope you enjoyed it, and I'll see you next time.